A definite integral evaluates to a single numerical value, but physically, that number describes a precise territory, the exact area trapped between a mathematical curve and the axis. This chart shows the probability density function of a normal distribution. In stochastics, the exact area shaded under this curve determines the real-world probability of an event. Precision here is the difference between a guess and a calculation. But standard integration creates a friction point known as oriented area. If a function dips below the x-axis, the calculus treats that space as negative. If we calculate a wave that spends equal time above and below the axis, the integral might return 0, even though the physical area is clearly there. To find the true geometric size, we have to perform a visual flip. We identify the roots, the Nullstellen, where the curve crosses the axis. Then we split the integral at these points and take the absolute value of each section. By forcing every piece to be positive, we recover the true total area. By breaking our calculations into absolute pieces, we turn abstract orientation into measurable physical space. Real-world problems are rarely bounded by a flat axis. Often, we need to find the territory trapped between two moving boundaries, two different functions, f of x and g of x. Take parabolas f of x and g of x. We must calculate the area of their overlap. We simplify this with a difference function. Subtracting g of x from f of x flattens the lower boundary to the axis. The curves become a single function. H of x equals 6x squared plus 6x minus 12. Don't worry about which function is on top. If you subtract the wrong way and get a negative result, the absolute value will correct it. The geometric area remains identical regardless of the order. By setting our functions equal to each other, we find our intersection points at x equals -2 and x equals 1. These become our limits of integration. Evaluating the integral of our difference function between those 2 points gives us an area of exactly 27. The difference function lets us box in any irregular shape by treating one boundary as a stable floor. We can even measure shapes that never actually end. Some mathematical territories stretch infinitely along the axis, yet they still contain a finite, measurable area. This is the Verteilungsfunction, function, the cumulative distribution. As the curve moves toward infinity, it approaches a horizontal limit of 1. This infinite stretch is the only way to calculate a total probability of 100%. To calculate this, we have to break the habit of treating infinity like a normal number. You can't plug a symbol into an equation. Instead, we use a placeholder variable, b, to represent a finite stopping point that we can push further and further out. We use limit notation, the limit as b approaches infinity for the integral from 1 to b. If we integrate the function 1 over x squared, we create an equation where the boundary b is a moving target. The antiderivative is -1 over x. When evaluated at b, we get -1 over b. As b grows infinitely large, that fraction vanishes to 0. All that's left is a total area of exactly 1. The limit is the only mathematically valid way to define the infinite. It's what allows modern statistics to turn endless curves into reliable data. Keep in mind that not every infinite shape is finite. While 1 over x squared converges to 1, the area under 1 over x grows forever. Only the limit test tells us which is which. To master area, follow this protocol. Find your roots and intersections. Use a difference function to simplify your boundaries. Take absolute sums to avoid cancellations. And if a shape stretches to the edge of the graph, use a limit to find its value. Sum the distribution of probability to the overlap of parabolas. The world is shaped by these precise geometric limits. By defining the intersections and testing the limits, we turn infinite complexity into a single, reliable number.